Hello everyone, this is our second lecture on chapter 14, kinetics of particle work and energy. Today we're going to talk about principle of work, energy, how to connect work with energy, and how can we apply this concept to find maybe a final velocity of a particle where the force is acting and it's moving along a direction. So let's see our learning objective today is develop the principle of work and energy. Some example would be in the image you see the car is skidding. So how we can apply the concept, so how far on the car may go before it stops, and what would be the final velocity if we know how far it will go before it stops. What would be the final velocity of the car given that it was the force was acting and some work being done. And also the same concept can be applied on a cart where if we're moving a cart, how friction is acting against the movement of the cart, and if we know the final velocity after application of force, so how far it will move, those kind of scenario. So let's start formulating our equations. The principle of work and energy. So let's start with an example. Assume that there is a path where a particle is moving. The initial position of the particle is 1. Final position or another position of the particle, we can assume it is 2. Currently the particle is located here. There could be a lot of force acting on that particle. F1, multiple forces acting, F2 and F3. So when there's a lot of forces, what do? We took a resultant force. So assume the resultant force F is acting along this direction, and the particle is moved a small distance ds. So we know if we want to consider for work, that is our goal, we have to take the component of the force along the path of the displacement. So we're going to take a tangent of that force. We could define it with Ft and assume that makes an angle theta with the force, duration of the force. So there will be a normal component F1n, and we're not interested into the normal component Fn. We're only interested in the tangential component of the force because it is acting along the direction of the particle movement, which is, we assume, a small distance ds. So and also assume that at the current position the particle has a velocity v. So now we're going to apply the Newton's second law of motion. So Ft, force equals to mass into acceleration. So tangential force will be equals to mass into tangential acceleration. To formulate the principle of work and energy, we need another equation today, and we have to go back to our chapter 12. When we had the kinematics, kinematic equation that we have derived during in that chapter, which is acceleration, in this case tangential acceleration, multiplied by at ds equals to v, velocity and change in velocity. So we're going to use this equation 1 and 2 to formulate the principle of work. Since it's to find the work, we know that force into distance is the work. So since it's a curved path, we're gonna do integration. So any final position S2, any initial position S1, and we're using the summation of force will be equals to VdV. So in this part we'll have so this is the work we need to find, and now we're going to start with equation 2. So from here we had AT ds equals to VdV. We're going to take integration on both sides, and we're going to replace this AT from this equation. So AT, acceleration in tangential direction, would be Ft over m. So this will become Ft ds, and now I'm gonna take the m on the other side, so mv dv, and we'll have our integration. So this is our target because that will lead us to our work. So we need this. We started with this equation, and then we plug the value from equation 1, and we got this relationship. If so, m is constant. We all know this mass is constant. So if we take integration, we will have the summation of force, integration from different initial position S1 to S2, Ft ds, and if we take integration on the other side, we will have integration of v dv, which will give us half v2 square minus half v1 square. Since we're doing a derivative integration with v, so it will have a limit of v2, v1, s1, s2. So if we simplify this equation, we will have on the left side the s2, s1, f t ds, and on the other side half m v2 square minus half m v1 square. Now this force into distance here is the work, so we're gonna say this is work from point 1 to point 2, and we're gonna term this this half m v2 square as a t2 and half m v1 square as t1. So this is our principle of work and energy. So this is the work, and t1 and t2 are kinetic energy. So this is also kinetic energy. So both are kinetic energy, but for different position. One thing to notice, and in our previous lecture we saw that the work can be negative or positive depending on the direction of the force and the direction of the movement of the particle. But kinetic energy, you see, is always square, so velocity, and no matter which direction, is square, and mass is positive, so kinetic energy is always positive. So that's one thing to remember. So this is This can be also written as T1 plus summation of U12 plus T2. So this is also a form of the principle of work and energy, which tells us that the initial kinetic energy and summation and the change of work. So if a particle had the initial kinetic energy of T1 and some work being done from a current position to a new position 2, which is summation of work done U12, that will be equal to the final kinetic energy that the particle has, which is T2. So this is the principle of work and energy. In next class, we're gonna see how this principle can be applied for system of particles and also friction. So see you in next class. Till then, thank you.